Hello, and welcome to the Quiet Cosmos. If you enjoy calm journeys through the deepest mysteries of the universe, take a moment to like the video, subscribe to the channel, and let me know where you're watching or listening from tonight. Whether you're in a quiet city apartment, a countryside home under dark skies, or listening with headphones somewhere halfway across the world, it's always fascinating to think that the same universe stretches above all of us. And somewhere out there, perhaps thousands, millions, or even billions of light years away, there are objects so strange that they seem to erase their own past. Black holes. They are born from some of the most chaotic and complex events in the cosmos. Massive stars collapse in violent supernova explosions. Matter twists, spins, and falls inward at incredible speeds. Magnetic fields tangle. Nuclear reactions rage. Entire stellar structures are crushed under gravity. Yet when the dust settles, something remarkable happens. From the outside, the black hole that remains appears almost unbelievably simple. No matter how complicated the original star was, no matter what elements it contained, no matter how violently it collapsed, physicists say that the black hole remembers almost nothing about it. In fact, according to one of the most elegant ideas in modern physics, a black hole can be completely described by just three numbers: its mass, its spin, and its electric charge. Everything else, all the details, all the history, disappears from view. This strange idea became famous through a phrase coined by physicist John Archibald Wheeler. He said simply, "Black holes have no hair." It's a curious phrase, a slightly humorous one even. But behind it lies a profound truth about gravity, space-time, and the deep mathematical structure of the universe. Because in almost every other object we know, from planets to stars to galaxies, the details matter. Shape matters, composition matters, history matters, but black holes seem different. They are the ultimate cosmic simplifiers, objects so extreme that they strip away complexity itself. Tonight, we're going to slowly explore why. We'll travel from the early days of Einstein's theory of general relativity to the first mathematical descriptions of black holes, through the violent physics of collapsing stars, and into the strange modern world of gravitational waves, quantum information, and the possibility that space-time itself may emerge from deeper laws. Along the way, we'll see why black holes appear so simple, why that simplicity might hide something even deeper, and why some physicists suspect the universe may still be keeping a few secrets hidden behind the horizon. So wherever you are listening from tonight, settle in, relax, and let's begin our journey into one of the quietest and most mysterious ideas in all of physics. Why do black holes have no hair? Somewhere in the vast darkness of the universe, there are objects so extreme that they quietly erase their own past. They begin their existence in chaos. Inside a massive star, layers of different elements are stacked like the skins of an onion. Hydrogen fuses into helium. Helium fuses into carbon. Carbon becomes heavier elements step by step, building an intricate chemical structure forged through millions of years of nuclear reactions. Temperatures in the core can reach tens of millions of degrees. Magnetic fields twist through the stellar plasma. Turbulence churns slowly through immense regions of hot gas. A star like this is not simple. It is a complicated, dynamic system containing enormous detail. Its mass might be many times that of our Sun. Its interior contains a record of nuclear history. Different elements sit in layered shells. Convection currents rise and fall through the stellar interior. Magnetic forces ripple through its atmosphere. In other words, a massive star carries a tremendous amount of information about itself. And yet, if that star collapses to form a black hole, something remarkable happens. All of that complexity disappears from view. From the outside universe, the black hole that remains appears astonishingly simple. In fact, according to one of the most elegant ideas in modern physics, it can be described by only a few basic properties: its mass, its spin, and its electric charge. That is all. Everything else that once defined the star seems to vanish behind the boundary of the black hole. The chemical composition, the magnetic field structure, the internal turbulence, even the details of how the star originally formed, all gone from external observation. This strange idea was captured by a phrase that has become one of the most memorable lines in theoretical physics. The American physicist John Archibald Wheeler once said, with characteristic brevity, that black holes have no hair. The phrase sounds playful, but the idea behind it is surprisingly deep. In this context, hair refers to any additional distinguishing feature that might allow one black hole to be identified as different from another. If black holes had hair, then the details of the collapsing star might leave observable traces in the final object. But according to the mathematics of general relativity, most of those details are smoothed away during collapse. What remains is something almost minimalist. A black hole becomes an object defined by only a handful of measurable numbers. To understand why this happens, we need to step back for a moment and look at the theory that first predicted the existence of black holes. That theory is general relativity, developed by Albert Einstein in the early 20th century. In everyday life, gravity feels familiar. Objects fall downward. Planets orbit stars. The moon circles the Earth. For centuries, gravity was described as a force that pulls masses toward each other, an idea formulated most famously by Isaac Newton. But Einstein introduced a radically different perspective. In general relativity, gravity is not a force in the traditional sense. Instead, massive objects change the very geometry of space and time. They bend space-time. Imagine placing a heavy ball onto a stretched rubber sheet. The sheet dips under the weight, and smaller objects rolling across the surface will naturally curve toward the dip. In Einstein's theory, something similar happens with space-time itself. Mass tells space-time how to curve, and curved space-time tells matter how to move. This idea can be expressed mathematically through the Einstein field equations. These equations describe how matter and energy influence the curvature of space-time, and how that curvature determines the motion of objects. The equations themselves are famously compact, though their implications are vast. In simple terms, they say that the distribution of matter and energy determines the geometry of space-time. One common way physicists summarize this relationship is with a phrase often attributed to physicist John Wheeler himself. Matter tells space-time how to curve, space-time tells matter how to move. Not long after Einstein published the equations of general relativity, scientists began exploring what kinds of cosmic objects those equations might allow. One of the first people to find a remarkable solution was a German physicist named Karl Schwarzschild. In the year 1916, while serving as an officer on the Eastern Front during the First World War, Schwarzschild studied Einstein's equations and discovered something extraordinary. He found the first exact mathematical solution describing the gravitational field surrounding a perfectly spherical mass. When Schwarzschild analysed the equations carefully, he realised that if enough mass were compressed into a small enough region of space, space-time would curve so severely that nothing could escape from it, not even light. The boundary surrounding such an object is now known as the Schwarzschild radius. If an object's entire mass were compressed within that radius, it would form what we now call a black hole. At the time, this result was mostly treated as a mathematical curiosity. Many physicists suspected that such an extreme configuration might never occur in nature. After all, compressing an entire star into such a tiny region seemed almost unimaginable. But as the 20th century progressed, astronomers began to understand that massive stars eventually run out of nuclear fuel. Without the outward pressure of fusion reactions supporting them, gravity takes over. The star begins to collapse. And if the collapsing core becomes dense enough, the mathematics of general relativity predicts that a black hole will form. What makes this process so fascinating is that it begins with tremendous complexity. A giant star is full of structure, motion, and energy. Yet the final object that emerges appears stripped of nearly all that detail. It's as though gravity itself acts like a cosmic eraser, smoothing away irregularities until only a few essential features remain: mass, spin, charge. This strange transformation raises a profound question. Why does the universe allow such violent events to produce objects that look so simple from the outside? And why does gravity, a force capable of shaping galaxies and bending light itself, seem to prefer this kind of elegant minimalism? The journey toward answering that question will take us through the mathematics of space-time, the collapse of massive stars, the ringing vibrations of newborn black holes, and even the strange intersection of gravity with quantum information. Because the deeper physicists look into black holes, the more it seems that their simplicity might not be the end of the story. It may in fact be the beginning of a deeper mystery hidden within the fabric of the universe itself. Long before black holes were accepted as real objects in the universe, the basic idea began as a quiet curiosity in the minds of a few 18th century thinkers. At the time, gravity was understood through the work of Isaac Newton. According to Newton's theory, every mass attracts every other mass through a force that grows stronger as objects become more massive and closer together. Newton's law of universal gravitation had already explained the motions of planets, the paths of comets, and the steady orbit of the Moon around Earth. But Newton's physics also implied something intriguing. If gravity becomes strong enough, it can prevent objects from escaping. To understand this, physicists use the idea of escape velocity. Escape velocity is the speed an object must reach in order to break free from the gravitational pull of another body without additional propulsion. For Earth, the escape velocity is about 11 kilometers per second. A spacecraft leaving Earth must eventually reach that speed to avoid falling back. For the Sun, escape velocity is much higher, roughly 600 kilometers per second at the solar surface. The escape velocity depends on two factors: the mass of the object producing gravity and the distance from its center. This relationship can be written as an equation describing the escape speed from a spherical body. In words, the formula states, escape velocity equals the square root of 2 times the gravitational constant, multiplied by the mass of the object divided by its radius. This equation comes directly from Newtonian mechanics and basic energy conservation. If the escape velocity becomes extremely large, something surprising happens. In the late 1700s, an English natural philosopher named John Michell considered this possibility. Michell was a geologist, astronomer, and one of the earliest thinkers to study gravitational effects in astronomy. In the year 1783, Michell published a letter to the Royal Society in London proposing a fascinating idea. He wondered what would happen if a star was so massive and so compact that its escape velocity exceeded the speed of light. At that time, light was widely believed to behave like a stream of tiny particles, sometimes called corpuscles. If gravity could pull on these particles, then a sufficiently massive star might trap its own light. Light would attempt to leave the surface, but gravity would pull it back. Such an object would appear completely dark to distant observers. Michell called these hypothetical objects dark stars. The idea was remarkably ahead of its time. Without knowing it, Michell had outlined the essential concept behind what we now call a black hole. His reasoning was based entirely on Newtonian gravity, yet the conclusion came surprisingly close to modern theory. A few years later, the French mathematician and astronomer Pierre-Simon Laplace independently proposed a similar idea. Laplace explored the same reasoning using Newtonian mechanics and suggested that the universe might contain stars whose gravity is strong enough to trap light. However, during the 19th century, the idea faded from scientific discussion. As wave theories of light became more accepted, many scientists concluded that gravity would not affect light in the way Michell and Laplace had imagined. The concept of dark stars quietly slipped into obscurity. It would take the revolutionary ideas of Albert Einstein to bring the concept back to life. In the early 20th century, Einstein developed the theory of general relativity. Instead of describing gravity as a force, Einstein proposed that gravity arises from the curvature of spacetime itself. Mass and energy change the geometry of space and time. Objects moving through that curved spacetime follow paths called geodesics, which are the natural straight lines within a curved geometry. Einstein's equations describing this relationship are known as the Einstein field equations. These equations relate the distribution of matter and energy to the curvature of spacetime. The structure of the equations can be summarized in words as a relationship between spacetime curvature and energy and momentum. One way physicists express this idea is through a simplified statement of the field equations. Spacetime curvature equals 8p times the gravitational constant divided by the speed of light, raised to the 4th power, multiplied by the energy momentum distribution. This compact mathematical statement describes how the universe bends and evolves under the influence of matter and energy. Soon after Einstein published his theory, scientists began searching for solutions to these equations. One of the first exact solutions came from Karl Schwarzschild. Schwarzschild was a German physicist and astronomer who found a solution in the year 1916 while serving in the German army during the First World War. Despite difficult conditions at the front, he managed to analyze Einstein's equations and discover a remarkably elegant result. Schwarzschild showed that the gravitational field around a perfectly spherical mass could be described by a specific mathematical solution. When this solution is examined closely, it reveals something remarkable. If a mass is compressed into a region smaller than a particular critical radius, space-time curvature becomes so extreme that nothing can escape. That critical boundary is now known as the Schwarzschild radius. For an object with the mass of our Sun, the Schwarzschild radius would be roughly 3 kilometers. In other words, if the entire Sun were somehow compressed into a sphere only a few kilometers across, it would become a black hole. At first, many physicists did not believe such objects could exist in reality. The mathematics of the Schwarzschild solution seemed valid, but it appeared to describe an unrealistic situation. Some scientists suspected that nature would always find a way to prevent such extreme compression. The apparent singularity in Schwarzschild's solution was also confusing. Early interpretations suggested that something strange happened at the critical radius, but it was not immediately clear whether this was a physical boundary or simply a coordinate artifact. For several decades, the idea of black holes remained mostly theoretical. Then, in the late 1930s, a crucial development occurred. Two physicists working in the United States began exploring what happens when a massive star exhausts its nuclear fuel. Their names were J. Robert Oppenheimer and Hartland Snyder. In the year 1939, they published a remarkable paper titled On Continued Gravitational Contraction. In this work, they analysed the collapse of a massive spherical star using Einstein's theory of general relativity. Their calculations showed that once nuclear pressure is no longer able to support the star, gravity takes over completely. The stellar core begins to collapse inward. As the collapse proceeds, space-time around the star becomes increasingly curved. Eventually, the collapsing matter passes within its Schwarzschild radius. At that moment, an event horizon forms. From the perspective of distant observers, the star appears to freeze and fade as light struggles to escape the intense gravitational field. Meanwhile, from the viewpoint of matter falling inward, the collapse continues inexorably toward a region of extreme density. Oppenheimer and Snyder had demonstrated that black holes were not just mathematical curiosities. According to general relativity, they could form naturally when massive stars collapse under their own gravity. At the time, however, the world's attention was focused elsewhere. The Second World War was approaching, and many physicists became involved in wartime research. Black hole studies temporarily slipped into the background, yet the groundwork had been laid. The early ideas of Michel and Laplace had introduced the possibility of stars so massive that light could not escape. Einstein's theory of general relativity had provided the mathematical framework for understanding gravity as curved space-time. Karl Schwarzschild had discovered the first exact description of a gravitational field capable of trapping light, and Oppenheimer and Snyder had shown that collapsing stars could naturally create these extreme objects. Together, these ideas quietly prepared the path for modern black hole physics. What began as a speculative thought experiment about dark stars had slowly evolved into one of the most profound predictions of Einstein's theory. And as astronomers and physicists continued to explore these ideas throughout the 20th century, they would discover that black holes were not rare mathematical oddities. They were woven into the very structure of the cosmos. One of the most important ideas in the study of black holes is something known as the event horizon. The phrase itself sounds almost poetic, but its meaning is precise and deeply rooted in the mathematics of general relativity. An event horizon is a boundary in space-time. It marks the point beyond which events can no longer influence the outside universe. In other words, anything that happens inside that boundary cannot send information outward to distant observers. Not light, not particles, not even signals moving at the maximum speed allowed by nature. To understand why this boundary exists, it helps to think again about how gravity works in Einstein's theory. In general relativity, gravity is not a force pulling objects inward in the traditional sense. Instead, massive objects change the geometry of space-time itself. Space and time bend together into a curved structure, and objects moving through that structure follow paths determined by the curvature. Those paths are called geodesics. A geodesic is the natural path an object follows when no other forces act on it. In everyday space, a straight line is the simplest example of a geodesic. But when space-time is curved by gravity, the straightest possible paths can become curved. This curvature becomes especially dramatic near a black hole. As matter collapses into a sufficiently compact region, space-time bends more and more steeply. Close to the center of the collapsing object, the curvature becomes extreme. Paths that once allowed light to escape begin to tilt inward. Far from a black hole, a beam of light can travel in any direction. It can move outward into space, or inward toward the gravitational source. But as the gravitational field strengthens, the outward paths begin to narrow. Eventually, a critical boundary forms. At this boundary, every possible path that light could take still leads inward. This boundary is the event horizon. To an observer far away, the event horizon represents the edge of the black hole. It is not a physical surface like the surface of a planet or star. There is no solid material there. Instead, it is a geometric boundary within space-time itself. Crossing that boundary does not feel like hitting a wall. In fact, if someone were falling toward a sufficiently large black hole, they might not notice the exact moment they passed the horizon. Yet from the perspective of the outside universe, that crossing is extremely significant. Once something moves inside the event horizon, it can no longer send signals outward. Light emitted from within the horizon will never reach distant observers. Instead, it remains trapped within the curved geometry surrounding the black hole. The escape velocity at the event horizon is equal to the speed of light, and because nothing can travel faster than light, escape becomes impossible. This boundary creates a profound separation between two regions of space-time. One region can communicate with the outside universe, the other cannot. Understanding how such boundaries form required deeper insights into the structure of space-time itself. In the 1960s, an important breakthrough came from a mathematician and physicist named Roger Penrose. Penrose was interested in the geometry of space-time and the behavior of light rays within curved gravitational fields. To study these ideas, he developed powerful mathematical tools that allowed physicists to analyze the global structure of space-time rather than focusing only on small local regions. One of Penrose's key innovations was the use of trapped surfaces. A trapped surface occurs when gravity becomes so strong that even light emitted outward from a surface begins to converge inward. Instead of spreading outward as light normally does, the rays are forced towards smaller regions of space. The presence of a trapped surface indicates that gravitational collapse has reached a critical stage. Once such a surface forms, Penrose demonstrated that the collapse cannot simply reverse itself. Instead, the mathematics of general relativity predicts that space-time will continue collapsing toward a singularity. A singularity is a region where the curvature of space-time becomes extremely large, and where current physical theories can no longer fully describe what happens. Density and gravitational forces grow without bound as the collapse proceeds. In 1965, Penrose published a groundbreaking paper showing that under very general conditions, gravitational collapse inevitably leads to singularities. His work did not depend on perfectly symmetrical stars or idealized assumptions. Instead, Penrose showed that singularities are a natural outcome of Einstein's equations whenever sufficient mass is compressed into a small region. This result transformed the way physicists understood black holes. Before Penrose's work, singularities were often dismissed as strange mathematical artifacts that might disappear under more realistic conditions. Penrose demonstrated that they were likely unavoidable. Soon after, Stephen Hawking extended Penrose's ideas. Working together, Hawking and Penrose developed what are now known as the singularity theorems. These theorems describe the conditions under which space-time must contain singularities. One version of the theorem states that if a sufficient amount of matter collapses under its own gravity, and if certain reasonable assumptions about energy and causality are satisfied, then space-time must develop a region where curvature becomes infinite. In simpler terms, once gravitational collapse passes a certain threshold, the formation of a singularity becomes inevitable according to classical general relativity. The event horizon plays a crucial role in this picture. It acts as a kind of one-way boundary surrounding the singularity. Outside the horizon, space-time remains connected to the wider universe. Inside the horizon, all possible future paths lead deeper toward the central singularity. The horizon therefore hides the most extreme regions of space-time from external observation. This feature has an important consequence for the study of black holes. Because the event horizon prevents information from escaping, distant observers cannot directly see what happens inside the black hole. The details of the collapsing matter become hidden from view. From the outside, only the properties that affect space-time outside the horizon remain visible. This is one reason why black holes appear so simple. The horizon acts as a kind of cosmic curtain, concealing the complex interior processes that may be unfolding within. Yet that same boundary also raises profound questions. If information about the collapsing star disappears behind the event horizon, what ultimately happens to it? Does the information remain stored somewhere inside the black hole? Is it somehow encoded on the horizon itself, or could it be lost entirely? These questions lie at the heart of one of the deepest puzzles in modern theoretical physics. The event horizon, which first appeared as a mathematical boundary in Einstein's equations, has become a gateway to some of the most fundamental mysteries about gravity, quantum mechanics, and the nature of information in our universe. Before a black hole appears, something dramatic must happen. A star must lose its long struggle against gravity. For most of a star's life, gravity and nuclear fusion exist in a delicate balance. Gravity constantly pulls the star inward, trying to compress its immense mass toward the center. At the same time, nuclear fusion deep inside the core produces enormous pressure pushing outward. This outward pressure comes from nuclear reactions where lighter atomic nuclei combine to form heavier ones. The most familiar example is the fusion of hydrogen into helium. In the core of our Sun, roughly 600 million tons of hydrogen are converted into helium every second, releasing energy according to Einstein's famous relationship between mass and energy. That relationship can be written in words as the equation energy equals mass multiplied by the speed of light squared. Although the amount of mass converted in each reaction is small, the speed of light squared is an enormous number. This allows nuclear fusion to release vast amounts of energy from tiny amounts of mass. For millions or even billions of years, this energy holds gravity at bay, but fusion cannot continue forever. As a star burns through its nuclear fuel, the chemical structure of its interior gradually changes. Hydrogen becomes helium. Helium may fuse into carbon and oxygen. In very massive stars, the chain of reactions continues further, producing neon, magnesium, silicon, and eventually iron. Iron is a special case in nuclear physics. Fusing iron into heavier elements does not release energy. Instead, it requires energy. When a star's core becomes dominated by iron, fusion can no longer provide the outward pressure needed to resist gravity. At that moment, the balance begins to fail. Gravity starts to win. The core begins to collapse inward under its own weight. For stars several times more massive than the Sun, this collapse can become extraordinarily violent. The core shrinks rapidly, and the density rises to incredible levels. A single teaspoon of such material could weigh billions of tons under those conditions. For a brief moment, another form of pressure can temporarily halt the collapse. This pressure comes from quantum mechanics and is known as neutron degeneracy pressure. According to the Pauli exclusion principle, two identical fermions cannot occupy the same quantum state. Neutrons belong to this category of particles, and when matter is compressed to extremely high densities, the neutrons resist being forced into identical states. This resistance generates a powerful form of pressure. If the collapsing core contains less than a certain critical mass, neutron degeneracy pressure can stabilize the object, producing what astronomers call a neutron star. But if the core becomes too massive, even this extraordinary pressure cannot stop gravity. This critical threshold was studied in detail during the late 1930s by physicists Richard Tolman, J. Robert Oppenheimer, and George Volkoff. Their calculations established what is now known as the Tolman-Oppenheimer-Volkoff limit. This limit represents the maximum mass a neutron star can possess before gravity overwhelms neutron degeneracy pressure. Although the precise value depends on the internal physics of neutron matter, modern estimates place the limit at roughly 2 to 3 times the mass of our Sun. If a collapsing stellar core exceeds this threshold, there is no known force capable of stopping the collapse. Gravity drives the matter inward without resistance. The core contracts rapidly, and the surrounding layers of the star respond in dramatic ways. When the collapsing core reaches nuclear densities, the outer layers of the star can rebound violently, producing a powerful explosion known as a core collapse supernova. These supernovae are among the most energetic events in the universe. For a brief period, a single exploding star can shine brighter than an entire galaxy containing billions of stars. The explosion releases an immense burst of neutrinos, along with shock waves that blast the outer layers of the star into space. Heavy elements forged in the star's interior are scattered across the surrounding interstellar medium. The calcium in human bones, the iron in human blood, and many other elements on Earth were created in such stellar explosions long ago. Meanwhile, deep at the center of the collapsing star, the story continues. If the core's mass remains below the Tolman-Oppenheimer-Volkoff limit, the collapse halts and a neutron star is born. But if the mass exceeds that limit, gravity continues pulling inward relentlessly. The collapsing core shrinks further and further. Eventually, it becomes so compact that its radius falls within the Schwarzschild radius associated with its mass. At that moment, an event horizon forms. A black hole is born. The conditions during this process are almost unimaginably complex. The interior of a massive star contains layers of different elements formed through nuclear fusion over millions of years. Turbulent convection currents carry heat and matter through the stellar interior. Magnetic fields twist and reconnect through highly energetic plasma. Rotation adds another layer of complexity. Many stars spin, sometimes rapidly. This rotation influences how matter moves during collapse, shaping the final dynamics of the explosion. In addition, shock waves travel through the collapsing material. Neutrinos stream outward from the dense core in enormous numbers. In fact, during a core collapse supernova, roughly 99% of the gravitational energy released is carried away by neutrinos. For a brief moment, the environment around the collapsing core becomes one of the most extreme laboratories in the universe. Temperatures can reach billions of degrees. Matter is compressed to densities exceeding those found inside atomic nuclei. Magnetic fields can grow strong enough to influence the motion of charged particles across enormous distances. All of this activity unfolds within a region only tens or hundreds of kilometers across. And yet, once the collapse is complete and the event horizon forms, an extraordinary transformation occurs. From the outside universe, almost none of this complexity remains visible. The violent turbulence, the layered chemical composition, the chaotic motion of plasma, and the details of the supernova explosion all fade from view. Instead, the newly formed black hole presents itself as something almost austere in its simplicity. A distant observer measuring the gravitational field will find that it depends only on a few quantities: the total mass of the black hole, the rate at which it spins, and in principle, its electric charge. Everything else that once defined the star appears to be hidden behind the event horizon. This leads to a profound puzzle. A massive star begins as a richly structured object filled with detail and complexity. Its interior carries the record of millions of years of nuclear reactions. Its magnetic fields and turbulent flows create intricate patterns of motion. Yet after gravitational collapse, the black hole that remains seems to have forgotten nearly all of that history. How can the universe take something so complicated and turn it into something so simple? That question lies at the heart of the mysterious principle that black holes appear to have no hair. When a massive star collapses into a black hole, the transformation is anything but quiet. The collapse is violent, chaotic, and filled with motion. Vast amounts of matter surge inward while shock waves ripple outward. Magnetic fields twist and reconnect. Neutrinos stream away in unimaginable numbers, and during this process, something else happens as well. The collapse of matter shakes space-time itself. According to Einstein's theory of general relativity, accelerating masses can produce ripples in the fabric of space-time. These ripples travel outward at the speed of light and are known as gravitational waves. Gravitational waves are not waves moving through space in the ordinary sense. Instead, they are tiny oscillations in the geometry of space-time itself. As a gravitational wave passes through a region, distances between objects stretch and shrink ever so slightly. The effect is extraordinarily small. Even the strongest gravitational waves detected on Earth change the length of a 4-kilometer detector arm by less than the width of a proton. Yet despite their subtlety, gravitational waves carry enormous information about violent astrophysical events. Whenever massive objects accelerate in an uneven or asymmetric way, gravitational waves are produced. A perfectly symmetrical collapse would not radiate gravitational waves. If a star collapsed in flawless spherical symmetry, every part of the star would move inward identically. In that situation, the gravitational field would remain perfectly balanced, and space-time would not generate waves, but real stars are rarely so tidy. Astrophysical objects contain turbulence, magnetic fields, rotation, and irregular distributions of matter. These asymmetries mean that as the star collapses, its gravitational field changes in complex ways. The shifting mass distribution sends ripples outward through space-time. Those ripples carry energy away from the collapsing system, and as they travel outward into the universe, they also carry away information about the distortions in the gravitational field. In effect, gravitational waves act like a natural smoothing mechanism. They allow space-time to shed complicated irregularities during collapse. The result is that the newly formed black hole gradually loses many of the complex distortions inherited from the collapsing star. This process becomes especially clear once the event horizon forms. Immediately after a black hole is created, it is not perfectly stable. The geometry of space-time surrounding the black hole still contains distortions left over from the chaotic collapse. These distortions cause the black hole to vibrate in characteristic ways. Physicists sometimes compare this behavior to the ringing of a bell. Strike a bell with a hammer, and it begins to vibrate. The metal oscillates, producing sound waves that gradually fade as energy is carried away through the air. A newly formed black hole behaves in a somewhat similar fashion, although instead of producing sound waves, it produces gravitational waves. These vibrations are described by a set of oscillations known as quasi-normal modes. The term quasi-normal means that the oscillations are not perfectly stable. Instead, they gradually fade over time as energy is radiated away. One of the first scientists to study these vibrations in detail was an Indian physicist named Chandrasekhar Venkata Vishveshwara. During the 1970s, Vishveshwara analysed how disturbances around a black hole evolve according to Einstein's equations. His work showed that black holes possess a distinctive set of vibration patterns determined only by their mass and rotation. Each oscillation mode has a characteristic frequency and decay rate. When a black hole is disturbed, these modes dominate the gravitational waves emitted during the final stages of collapse. The phenomenon became known as black hole ringing. Over time, the vibrations fade as gravitational waves carry energy away into space. As the oscillations decay, the distortions in space-time gradually disappear. Eventually, the black hole settles into a stable configuration. This final stage of the process is known as the ring-down phase. During ring-down, the black hole emits gravitational waves with very specific frequencies. These frequencies depend only on a few properties of the black hole itself. The most important factors are the black hole's mass and its angular momentum, which describes how quickly it is rotating. Remarkably, the details of the collapsing star do not affect these final vibrations. Whether the star originally had strong magnetic fields, turbulent motion, or complex chemical layers makes no difference once the black hole settles down. The gravitational waves emitted during ring-down reflect only the fundamental parameters of the black hole. This behavior provides one of the strongest pieces of evidence for the simplicity of black holes predicted by general relativity. In recent years, this prediction has even been tested directly through observation. In the year 2015, the Laser Interferometer Gravitational Wave Observatory, often called LIGO, detected gravitational waves produced by the merger of two black holes. The detectors are located in the United States, with facilities in the states of Louisiana and Washington. LIGO works by using laser interferometry to measure incredibly tiny changes in distance caused by passing gravitational waves. Two long vacuum tubes form perpendicular arms, and laser beams bounce between mirrors inside them. When a gravitational wave passes through the detector, the length of the arms changes slightly, altering the interference pattern of the laser light. The first detection revealed gravitational waves from two merging black holes located more than 1 billion light-years away. After the merger, the newly formed black hole entered a ring-down phase. Its gravitational waves faded away in precisely the pattern predicted by the theory of quasi-normal modes. Subsequent detections by LIGO and its European partner observatory Virgo have confirmed similar signals from other black hole mergers. Each time, the ring-down phase behaves exactly as Einstein's theory predicts. The vibrations decay, the distortions vanish, and the black hole settles into a stable geometry defined only by a few measurable properties. In this way, gravitational radiation gradually erases the complicated structure left over from collapse. Irregularities in space-time are carried away as waves, distorted regions smooth themselves out, and the black hole approaches a remarkably simple final state. From a distance, the object that remains looks almost minimalist compared with the turbulent star that once existed. Its gravitational field depends only on its mass and rotation. All the messy details of the star's previous life seem to have faded away. Gravity, it appears, has quietly swept the stage clean. As physicists began to explore the strange simplicity of black holes, one phrase eventually captured the idea in a way that was both memorable and surprisingly playful. The phrase was introduced by the American theoretical physicist John Archibald Wheeler. Wheeler had a gift for vivid language. He helped popularize many of the terms that now feel completely natural in modern physics. The word black hole itself was championed by Wheeler in the late 1960s, replacing earlier descriptions such as gravitationally completely collapsed object. But perhaps his most famous remark about black holes was even shorter. Black holes, Wheeler said, have no hair. At first hearing, the statement sounds almost like a joke. It conjures up an image of something perfectly smooth, perhaps even slightly comical. But behind that simple phrase lies a deep and very specific physical idea. In this context, hair represents any additional detail that might allow one black hole to be distinguished from another. Imagine two stars collapsing under gravity. Before the collapse begins, those stars may be enormously different. One might rotate rapidly, while the other spins slowly. One might contain strong magnetic fields, while the other has weaker ones. Their interiors could have different chemical compositions, different temperature structures, and different histories of nuclear fusion. In ordinary astrophysical objects, those differences matter. If astronomers study two stars carefully, they can often determine a great deal about their structure and history. The spectrum of light emitted by a star reveals the chemical elements present in its atmosphere. Variations in brightness can reveal rotation and magnetic activity. Surface temperatures and densities provide clues about the processes occurring deep inside. Stars, planets, and galaxies all carry rich information about their past. But black holes appear to behave very differently. Once a collapsing object forms an event horizon and settles into equilibrium, the external gravitational field seems to forget almost everything about the matter that created it. The turbulence of the collapsing star disappears from view. The internal layering of elements becomes hidden. Even the detailed shape of the collapsing matter fades away. What remains visible to distant observers is something much simpler. According to the predictions of general relativity, a stationary black hole can be fully described using only a small number of measurable properties. The most important of these properties is mass. Mass determines how strongly the black hole curves space-time around it. A more massive black hole creates a deeper gravitational well and influences objects at larger distances. The second property is angular momentum, which describes how quickly the black hole rotates. Rotation affects the geometry of space-time in fascinating ways. A spinning black hole drags space-time around with it, a phenomenon known as frame dragging. This effect was predicted by general relativity and has been studied in detail around rotating black hole solutions. The third possible property is electric charge. In principle, a black hole could carry electric charge if the collapsing matter contains an imbalance between positive and negative charges. However, in most astrophysical situations, electric charge quickly neutralizes as surrounding matter falls into the black hole. As a result, most real black holes are expected to have almost no net electric charge. So in practice, astrophysical black holes are usually described by just two numbers, mass and spin. That is an astonishing reduction in complexity. Consider again the star that formed the black hole. Its interior contained an enormous amount of information, billions upon billions of atoms arranged in intricate patterns, layers of different elements produced through nuclear fusion, magnetic fields twisting through plasma, turbulent currents carrying heat through the stellar interior. Yet when the collapse is complete, the black hole that remains seems to have forgotten nearly all of it. If two stars with completely different compositions collapse into black holes with the same mass and the same rotation rate, the resulting black holes will appear identical to distant observers. There will be no visible trace of their original differences. This idea suggests that gravitational collapse acts like a kind of universal simplifier. As matter falls inward, gravitational radiation carries away distortions in space-time. Irregularities smooth out, oscillations fade. Eventually, the geometry settles into a stable configuration that depends only on a few basic parameters. In a sense, gravity combs the hair out of the collapsing star until nothing remains but a smooth gravitational field. The phrase "no hair" therefore captures the idea that black holes lack distinguishing features beyond their fundamental parameters. Yet physicists wanted more than a memorable phrase. They wanted to know whether this idea could be proven mathematically. If general relativity truly predicts that black holes have no hair, then the equations describing spacetime should reveal this simplicity directly. Throughout the 1960s and 1970s, several researchers began examining the mathematical structure of Einstein's equations to determine whether black holes truly settle into a limited family of solutions. Their work led to a set of results that became known collectively as the black hole uniqueness theorems. These theorems show that under certain assumptions, all stationary black holes in general relativity must belong to a specific class of solutions. Instead of an infinite variety of possible black hole structures, the equations appear to allow only a small number of possibilities. In other words, the mathematics itself seems to enforce simplicity, and as physicists explored these results more deeply, they began to realize that Wheeler's playful phrase was pointing towards something profound. The universe might contain objects so extreme that gravity strips away nearly all the information about their origins, leaving behind only a few essential numbers written into the curvature of space-time. If black holes truly erase most of the details of the stars that create them, an obvious question follows. What information does remain? According to classical general relativity, the answer is surprisingly concise. A black hole can be completely described by only three measurable quantities: its mass, its electric charge, and its angular momentum, which describes how fast it is rotating. These three properties determine the geometry of space-time surrounding the black hole. Everything that distant observers can measure about the black hole ultimately depends on these parameters. To appreciate why this is so remarkable, it helps to think again about how complicated ordinary objects are. Consider something as simple as a planet. Earth has mountains, oceans, continents, and a layered interior structure. Its gravitational field depends not only on its total mass, but also on how that mass is distributed throughout the planet. Even small irregularities matter. A mountain range slightly alters Earth's gravitational field in its vicinity. Satellite measurements can detect these variations and map the distribution of mass beneath the surface. Stars are even more complex. A typical star contains enormous temperature gradients, magnetic fields, turbulent convection currents, and multiple layers where different nuclear reactions occur. The gravitational field outside such an object reflects this complexity through a series of quantities known as multipole moments. Multipole moments describe how mass is arranged within an object. The simplest moment is the total mass, which determines the overall strength of gravity. Higher moments describe distortions from perfect symmetry. Black holes, however, appear to behave very differently. Once a black hole settles into a stable configuration, its external gravitational field contains no memory of the detailed mass distribution that once existed inside the star. The higher multipole moments vanish, leaving only those associated with mass and rotation. In essence, the complicated gravitational fingerprint of the original star fades away. Mass is the first and most fundamental property. Mass determines how strongly the black hole curves space-time. A more massive black hole produces a deeper gravitational well and influences objects at greater distances. The Schwarzschild radius, which defines the size of the event horizon for a non-rotating black hole, depends directly on mass. The relationship can be expressed through the Schwarzschild radius formula. In words, the equation states, the Schwarzschild radius equals 2 times the gravitational constant multiplied by the mass of the object divided by the speed of light squared. For an object with the mass of our Sun, this radius is roughly 3 kilometers. If the mass were 10 times greater, the Schwarzschild radius would grow to about 30 kilometers. Although these sizes sound small compared with ordinary stars, the gravitational influence of a black hole extends far beyond the horizon. The second defining property is electric charge. In principle, black holes can carry electric charge if the collapsing matter contains an imbalance between positive and negative charges. A charged black hole has a different spacetime geometry than an uncharged one. The solution describing such an object is known as the Reissner-Nordström solution, developed by physicists Hans Reissner and Gunnar Nordström in the early 20th century. In this solution, the electric charge modifies the structure of spacetime near the black hole and changes the positions of the event horizons. However, most astrophysicists believe that real black holes carry almost no electric charge. The reason is simple. Space is filled with charged particles such as electrons and protons. If a black hole developed even a small imbalance in electric charge, it would quickly attract particles of the opposite charge from its surroundings. These incoming particles would neutralize the charge very rapidly. Because this process happens so efficiently, astrophysical black holes are expected to remain nearly electrically neutral. That leaves the third defining property, angular momentum. Angular momentum measures how much an object is rotating. Most stars rotate to some degree, and when a rotating star collapses, The conservation of angular momentum causes the rotation rate to increase dramatically. This is similar to the way a figure skater spins faster when pulling their arms inward during a spin. As the collapsing star shrinks, its rotation accelerates. The result is a rotating black hole. For many years, physicists struggled to find an exact solution to Einstein's equations describing a rotating black hole. The mathematics of general relativity is notoriously complex, and incorporating rotation into the equations made the problem significantly more difficult. Then, in the year 1963, a New Zealand mathematician named Roy Kerr discovered the solution. The Kerr solution describes the space-time geometry surrounding a rotating black hole. It revealed that spinning black holes possess a remarkably rich structure. Unlike a non-rotating black hole, which is perfectly spherical, a rotating black hole is slightly flattened at the poles due to its spin. The rotation also drags space-time around with it, creating a phenomenon known as frame dragging. Frame dragging means that space-time itself begins to swirl around the rotating mass. Objects that move close to a rotating black hole are forced to co-rotate with the space-time around them. In certain regions, it becomes impossible for an object to remain stationary relative to distant stars. One particularly interesting region surrounding a rotating black hole is known as the ergosphere. The ergosphere lies outside the event horizon and has a distinctive shape somewhat like a flattened sphere. Within this region, frame dragging becomes so strong that every object must move in the direction of the black hole's rotation. The ergosphere allows for fascinating physical processes. For example, energy can be extracted from a rotating black hole through a mechanism known as the Penrose process, proposed by Roger Penrose. In this process, particles entering the ergosphere can split into two fragments. One fragment falls into the black hole, while the other escapes with greater energy than the original particle possessed. Although the Penrose process is difficult to observe directly, related mechanisms may help power some of the most energetic phenomena in the universe, such as relativistic jets emerging from supermassive black holes in active galactic nuclei. Despite these complexities, the overall description of a rotating black hole remains remarkably compact. The Kerr solution shows that the geometry of spacetime around the black hole depends only on two parameters, mass and angular momentum. Once those two quantities are specified, the entire external spacetime structure is determined. All the complicated details of the star that collapsed to form the black hole have disappeared from the external gravitational field. This result is one of the most striking features of general relativity. In almost every other branch of physics, complex systems retain traces of their past. Materials carry microscopic defects. Planetary surfaces record the history of impacts and geological processes. Even simple objects often preserve subtle fingerprints of their origins. Black holes appear to be different. Their external appearance is governed by only a few fundamental numbers: mass, spin, and in principle, electric charge. Everything else is hidden behind the event horizon, leaving behind one of the most elegant examples of simplicity, emerging from extreme complexity in the universe. The idea that black holes possess only a few defining properties might at first sound like a clever summary or a convenient approximation. But physicists did not want to rely on intuition alone. They wanted to know whether the mathematics of Einstein's theory truly forces black holes to be this simple. To answer that question, researchers began examining the structure of Einstein's field equations in great detail. The equations of general relativity are notoriously complex. They describe how the curvature of spacetime responds to the presence of matter and energy. Written in their full mathematical form, they contain 10 coupled nonlinear equations that relate the geometry of spacetime to the energy and momentum of whatever matter is present. Even writing the equations is a challenge. Solving them exactly is far more difficult. Despite this complexity, physicists gradually discovered that black hole solutions form a surprisingly small family. The external spacetime geometry surrounding a stationary black hole appears to follow very specific patterns dictated by the equations themselves. This realization eventually led to a collection of results known as the black hole uniqueness theorems. These theorems show that once a black hole settles into a stable state, its external spacetime must match one of only a few possible solutions of Einstein's equations. In other words, the equations of general relativity do not allow an infinite variety of black hole structures. Instead, they funnel gravitational collapse toward a very limited set of possibilities. One of the earliest and most important contributions to this understanding came from a physicist named Werner Israel. In the late 1960s, Israel examined the properties of non-rotating black holes. His goal was to determine whether the Schwarzschild solution truly represented the only possible geometry for a stationary non-rotating black hole. Using careful mathematical reasoning, Israel proved that if a black hole is static and surrounded by empty space, then the solution must be perfectly spherical. There is no room for irregular shapes. The event horizon must form a sphere, and the space-time outside the black hole must match the Schwarzschild solution exactly. This result was profound. It showed that once gravitational collapse settles down, any distortions or asymmetries must disappear from the external geometry. The mathematics of Einstein's equations enforces spherical symmetry for non-rotating black holes. The conclusion aligned beautifully with the idea that black holes have no hair, but most astrophysical black holes are not static. Stars rotate, and when they collapse, the resulting black holes inherit that angular momentum. A rotating black hole cannot be perfectly spherical. Instead, its geometry must reflect the effects of rotation. The question then became whether rotating black holes also follow a unique mathematical description. During the 1960s, the rotating black hole solution discovered by Roy Kerr had already shown that such objects could exist within general relativity. The Kerr solution described a rotating black hole characterized by mass and angular momentum. But was the Kerr solution the only possible rotating black hole solution? To answer this, physicists continued to investigate the structure of Einstein's equations. One of the key figures in this effort was Brandon Carter. Carter analyzed the symmetries and conserved quantities associated with rotating black holes. His work revealed that the Kerr solution possesses remarkable mathematical properties that allow particle motion around the black hole to be described with unusual precision. These properties suggested that the Kerr geometry might represent a very special solution. Stephen Hawking later extended these ideas by studying the properties of black hole horizons themselves. Hawking demonstrated that under reasonable physical assumptions, the event horizon of a stationary black hole must have a very specific structure. In particular, Hawking proved that the surface gravity of a stationary black hole must be constant across the horizon. Surface gravity describes the strength of the gravitational field at the horizon, and this uniformity turned out to be a key feature of black hole thermodynamics. Combining the insights of Israel, Carter, Hawking, and other researchers gradually built a powerful conclusion. If a black hole exists in a stationary state, meaning that it has settled down and is no longer changing with time, then its space-time geometry must match one of a very small number of exact solutions. A non-rotating black hole must follow the Schwarzschild solution. A rotating black hole must follow the Kerr solution. And if electric charge is included, the corresponding solutions become the Reissner-Nordström or Kerr-Newman geometries. Together, these results form the core of the black hole uniqueness theorems. But the mathematical exploration of black holes did not stop there. Several mathematicians and theoretical physicists continued pushing the analysis of Einstein's equations to deeper levels. Their work aimed to understand not just the existence of these solutions, but the stability and behavior of spacetime itself. One important contributor in this area is Dimitrios Christodoulou. Christodoulou studied the dynamics of gravitational collapse and the behavior of nonlinear waves in spacetime. His research helped clarify how black holes can form dynamically through realistic gravitational processes rather than idealized symmetric collapse. Another key figure is Sergei Kleinemann. Kleinemann made major contributions to the mathematical understanding of the Einstein field equations, particularly in proving the stability of Minkowski spacetime. Minkowski spacetime is the simplest solution of general relativity, representing empty space with no gravity. Demonstrating its stability required sophisticated analysis of how gravitational waves behave and how small perturbations evolve over time. These kinds of mathematical studies are essential because Einstein's equations are highly nonlinear. Small disturbances can evolve in complicated ways, and understanding whether solutions remain stable is a major challenge. Another mathematician who has contributed significantly to the study of black hole geometry is Piotr Kruszkiel. Kruszkiel has worked extensively on the rigorous classification of stationary black hole solutions and the mathematical structure of horizons. His research has helped strengthen the formal foundations of the uniqueness theorems and clarify the assumptions required for them to hold. Together, these efforts reveal something remarkable about the structure of general relativity. The simplicity of black holes is not merely a coincidence. It arises from the deep mathematical constraints built into Einstein's field equations. When massive objects collapse under gravity, the geometry of space-time evolves according to those equations. Distortions propagate outward as gravitational waves, irregularities smooth out. Eventually, the system settles into one of the few stable configurations allowed by the theory. In this way, the equations of general relativity act almost like a sculptor. No matter how complicated the original collapsing star may have been, the mathematical structure of spacetime gradually shapes the final result into a simple and highly constrained form. The remarkable outcome is that black holes emerge as some of the most mathematically elegant objects predicted by modern physics. They are born from chaos, yet governed by equations that insist on simplicity. To understand just how unusual black holes are, it helps to look at how gravity behaves around ordinary objects. One of the most powerful tools physicists use to describe gravitational fields is something called a multipole expansion. The word multipole might sound technical, but the basic idea is quite intuitive. A multipole expansion is a mathematical way of describing how mass is distributed inside an object by breaking the gravitational field into a series of components. Each component represents a different level of complexity in the mass distribution. The simplest term in this series is called the monopole moment. The monopole moment represents the total mass of the object. If all you know about an object is its total mass, then from far away its gravitational field looks roughly like the field of a point mass. But most real objects are not perfectly symmetrical. They may be slightly flattened, stretched, or irregular. To describe those features, physicists include additional terms called higher multipole moments. The next level is the dipole moment, which reflects an offset between the center of mass and the coordinate system being used. In most astrophysical situations, the dipole moment can be removed simply by choosing the coordinate system so that it sits at the center of mass. Beyond that comes the quadrupole moment. The quadrupole moment describes how much an object's shape deviates from perfect spherical symmetry. A planet that is slightly flattened at the poles due to rotation has a measurable quadrupole moment. Higher moments follow as well. Octupole moments, hexadecapole moments, and many more. Each additional term captures finer details of how mass is distributed inside the object. For planets and stars, these higher multipole moments contain a wealth of information. Take Earth as an example. Earth is not a perfect sphere. It bulges slightly at the equator because of its rotation. This bulging produces a measurable quadrupole moment in Earth's gravitational field. Satellites orbiting Earth experience tiny variations in gravity depending on their position relative to that bulge. Scientists use these variations to map Earth's internal structure and the distribution of mass across the planet. Stars show similar behavior. Their gravitational fields can reflect rotation, internal flows of matter, and deviations from spherical symmetry. If a star has large magnetic structures or uneven mass distributions, these can influence the multipole moments of its gravitational field. In other words, most astronomical objects carry a detailed gravitational fingerprint. But black holes are different. For a rotating black hole described by the Kerr solution, the multipole structure follows an astonishingly simple rule. All of the multipole moments of the black hole are determined entirely by just two numbers, its mass and its angular momentum. This relationship is known as the Kerr multipole relation. The rule can be expressed in words through a remarkably compact formula describing the sequence of mass and current multipole moments. In simplified language, the relation states that each multipole moment is determined by the black hole's mass multiplied by its spin raised to a particular power. Physicists sometimes summarize this idea with the following expression written in words. The multipole moment of order n equals the mass multiplied by the angular momentum raised to the power, n multiplied by the imaginary unit raised to the power mn. While the full mathematics involves complex numbers and tensor geometry, the physical meaning is straightforward. If you know the mass of the black hole and how fast it is spinning, you can calculate every multipole moment in its gravitational field. There is no additional freedom, no extra parameters, no hidden complexity. This is a striking contrast with ordinary stars and planets, which can have independent multipole moments reflecting their internal structure. A black hole's quadrupole moment, for example, is not independent. It is determined entirely by the mass and spin of the black hole. If you measure those two quantities, the quadrupole moment follows automatically. This feature provides an extremely powerful test of the idea that black holes have no hair. If astrophysical black holes truly obey the Kerr solution predicted by general relativity, then their multipole moments must follow this precise relationship. But if observations ever revealed a mismatch between the measured multipole moments and the predicted values, it could mean that the object is not a true Kerr black hole. Such a discovery would have profound implications for our understanding of gravity. Testing this prediction has become one of the goals of modern gravitational wave astronomy. When two black holes spiral toward each other and merge, they emit gravitational waves carrying detailed information about the geometry of space-time around them. The shape of the gravitational wave signal depends on the multipole structure of the black holes involved. By carefully analyzing these signals, scientists can measure properties such as mass, spin, and potentially even higher multipole moments. Several researchers have played important roles in developing these techniques. Emanuele Berti, a physicist known for his work in gravitational wave astrophysics, has studied how the vibrations of black holes encode information about their multipole moments. His research explores how gravitational wave detectors can test the Kerr nature of astrophysical black holes. Vitor Cardoso has also contributed extensively to the theoretical understanding of black hole perturbations and ring-down signals. His work has helped clarify how gravitational waves emitted during the final stages of a black hole merger reveal the properties of the newly formed object. Another researcher working in this field is Ryan O'Shaughnessy, who studies how gravitational wave observations can probe the dynamics and geometry of compact objects. By analysing the detailed structure of gravitational wave signals, scientists like O'Shaughnessy aim to extract precise measurements of black hole parameters. These efforts rely on the extraordinary sensitivity of modern detectors, such as the Laser Interferometer Gravitational Wave Observatory and its European counterpart Virgo. These observatories can detect distortions in space-time smaller than a fraction of a proton's width. With such precision, scientists are beginning to test the predictions of general relativity in the most extreme environments known. If the observed multipole moments of astrophysical black holes continue to match the Kerr multipole relation, it will provide powerful confirmation that black holes truly follow the elegant simplicity predicted by Einstein's theory. But if deviations are ever detected, it could signal the presence of new physics. Either way, the multipole structure of black holes offers a remarkable window into the deepest laws governing gravity and space-time. It allows scientists to test whether the universe truly produces objects with no hair at all, or whether subtle details remain hidden within the geometry of the cosmos. For many decades, black holes were studied almost entirely through mathematics. Physicists explored their properties using Einstein's equations, pencil and paper, and increasingly powerful computer simulations. The predictions were elegant and precise, but they remained largely theoretical. That situation changed dramatically in the early years of the 21st century. The key development was the direct detection of gravitational waves. Gravitational waves are ripples in space-time produced when massive objects accelerate in asymmetric ways. These waves travel outward at the speed of light, carrying information about the motion and structure of the objects that created them. Albert Einstein predicted their existence in 1916 as a consequence of general relativity. But for a century they remained extraordinarily difficult to detect because the distortions they produce are incredibly small. To measure them required instruments of astonishing sensitivity. One of the most ambitious efforts to detect gravitational waves was the Laser Interferometer Gravitational Wave Observatory, commonly known as LIGO. LIGO consists of two enormous observatories in the United States. One is located in Livingston, Louisiana, and the other in Hanford, Washington. Each facility contains an interferometer with two long vacuum tubes arranged at right angles. Laser beams travel back and forth along these arms, reflecting between precisely positioned mirrors. If a gravitational wave passes through the detector, the lengths of the arms change ever so slightly. The difference in distance is minuscule. The change is roughly 1/10,000th the diameter of a proton over a distance of 4 kilometers. Detecting such a tiny distortion requires extraordinary engineering precision and careful isolation from environmental vibrations. The project was developed over many decades, with major contributions from physicists including Rainer Weiss, Kip Thorne, and Barry Barish. Their leadership helped bring the ambitious experiment from early design concepts to a functioning observatory capable of measuring the faintest ripples in space-time. Finally, In the year 2015, the effort succeeded. On the 14th of September that year, LIGO recorded a signal that matched the predictions of general relativity with astonishing accuracy. The signal came from the merger of two black holes located more than 1 billion light-years away. Each of these black holes had a mass several tens of times greater than the mass of our Sun. As they spiraled toward one another, the pair emitted gravitational waves carrying energy away from the system. Over time, the orbit shrank and the two black holes moved faster and faster until they finally collided and merged. The signal detected by LIGO contained 3 distinct stages. The first stage was the inspiral, during which the two black holes orbited each other at increasing speed. The second stage was the merger itself, when the horizons of the two black holes combined into a single larger horizon. The final stage was something especially important. After the merger, the newly formed black hole did not immediately settle into its final shape. Instead, it vibrated. Those vibrations produced gravitational waves that gradually faded away over time. This final phase is known as the ringdown. The ringdown stage is closely related to the quasi-normal modes studied decades earlier by researchers such as Chandrasekhar Venkata Vishveshwara. Just like a struck bell that vibrates before becoming quiet again, the newly formed black hole oscillates as it releases its remaining distortions. Each oscillation mode has a specific frequency and damping rate, and here is where things become particularly interesting. The frequencies of these vibrations depend only on the mass and spin of the black hole. No other properties influence them. By measuring the gravitational wave frequencies during the ringdown phase, scientists can determine the mass and angular momentum of the final black hole with remarkable precision. In other words, the gravitational waves act like the sound of the black hole ringing, and just as the tone of a musical instrument reveals its size and shape, the ringing of a black hole reveals its fundamental parameters. This insight has led physicists to develop a powerful technique known as black hole spectroscopy. The name is borrowed from traditional spectroscopy in astronomy, where scientists analyze the light from stars to identify the chemical elements they contain. Each element produces a characteristic pattern of spectral lines. Black hole spectroscopy works in a similar spirit. Instead of analyzing light, scientists analyze the spectrum of gravitational wave frequencies emitted during the ringdown phase. If multiple vibration modes can be detected, their frequencies can be compared with the predictions of the Kerr solution of general relativity. Researchers such as Vitor Cardoso and Emanuele Berti have played leading roles in developing the theoretical framework for this technique. Their work has explored how future gravitational wave detectors might identify multiple oscillation modes and use them to test the properties of black holes with great precision. If the frequencies follow the pattern predicted by the Kerr geometry, it would confirm that the black hole is described completely by its mass and spin. But if additional modes appear that do not match the Kerr predictions, it could indicate that something more complicated is happening. Perhaps the object is not a true black hole, or perhaps the theory of gravity itself requires modification. For now, the signals observed by LIGO and its European partner Virgo have been consistent with the predictions of general relativity. The ringdown frequencies match the expected behavior of Kerr black holes remarkably well. Each observation strengthens the evidence that real black holes follow the elegant simplicity described by the no-hair principle. Yet the story is still unfolding. Future detectors with greater sensitivity may be able to measure additional oscillation modes and test the theory even more rigorously. With every gravitational wave detection, the universe is providing another opportunity to listen carefully to the ringing of black holes and to learn whether the cosmic objects that emerge from gravitational collapse truly carry no hair at all. As physicists studied black holes more closely during the 1970s, something unexpected began to emerge. At first, black holes appeared to be purely gravitational objects. They were solutions to Einstein's equations, defined by the geometry of spacetime and the collapse of massive stars. Their properties seemed to belong entirely to the domain of gravity. But gradually, researchers realized that black holes behaved in ways that closely resembled the laws of thermodynamics. Thermodynamics is the branch of physics that studies heat, energy, and entropy. It governs how energy flows through systems and how disorder evolves over time. These laws describe familiar processes such as steam engines, refrigerators, and the gradual spreading of heat through matter. At first glance, thermodynamics might seem completely unrelated to black holes. After all, a black hole is defined by gravity and spacetime geometry, not by temperature or heat flow. Yet a young physicist named Jacob Bekenstein began to notice a curious parallel. Bekenstein was a graduate student working under the supervision of John Wheeler at Princeton University. While studying black hole physics in the early 1970s, he realized that black holes seem to obey a rule reminiscent of the second law of thermodynamics. The second law states that the total entropy of an isolated system never decreases over time. Entropy is often described as a measure of disorder, or the number of possible microscopic arrangements corresponding to a macroscopic state. A cup of hot coffee gradually cools because energy spreads into the surrounding environment. As it does, the entropy of the system increases. Bekenstein noticed something intriguing about black holes. The area of a black hole's event horizon never decreases. This result had already been proven by Stephen Hawking through what became known as the area theorem. Hawking showed that, according to classical general relativity, the total area of black hole horizons can only stay the same or grow larger during physical processes such as mergers. Two black holes colliding will produce a final black hole whose horizon area is greater than or equal to the sum of the original areas. Bekenstein saw a striking resemblance between this rule and the second law of thermodynamics. If entropy always increases and black hole horizon area always increases, perhaps the area of a black hole was related to entropy itself. Bekenstein proposed a bold idea. He suggested that black holes possess entropy proportional to the surface area of their event horizons. This was a radical suggestion. Traditionally, entropy is associated with microscopic states inside a system, such as the positions and motions of atoms in a gas. But black holes appeared to hide their internal details behind the event horizon. Despite this mystery, Bekenstein argued that the entropy of a black hole must be proportional to its horizon area. The relationship can be written as an equation describing black hole entropy. In words, the formula states black hole entropy equals the area of the event horizon divided by 4 times the Planck length squared. The Planck length is an extremely small unit of distance defined by fundamental constants of nature. It is roughly 1.6 times 10 to the minus 35 meters. Because the Planck length is so tiny, dividing by its square produces an enormous number. As a result, even a modest-sized black hole contains an immense amount of entropy. For a black hole with the mass of our Sun, the entropy is roughly 10 to the 77 in units of Boltzmann's constant. That is far greater than the entropy of an ordinary star. At first, many physicists were skeptical of Bekenstein's proposal. The reason was simple. Entropy is normally associated with temperature, and temperature implies the emission of radiation. A hot object radiates energy into its surroundings. But black holes were believed to emit nothing. If nothing escapes from inside the event horizon, how could a black hole possibly have a temperature? Stephen Hawking initially criticized Bekenstein's idea for this reason. Yet when Hawking examined the problem more carefully using quantum theory, he discovered something extraordinary. In the year 1974, Hawking showed that black holes are not entirely black after all. When quantum mechanics is taken into account, black holes emit radiation. This effect arises because empty space is not truly empty. According to quantum field theory, even the vacuum contains fluctuating fields that constantly produce pairs of virtual particles and antiparticles. Near the event horizon of a black hole, these particle pairs can be separated by the intense gravitational field. One particle may fall into the black hole while the other escapes into space. To distant observers, it appears as though the black hole is emitting particles. This phenomenon became known as Hawking radiation. The radiation has a thermal spectrum, meaning it behaves exactly like the radiation emitted by a hot object with a specific temperature. The temperature of a black hole depends on its mass. In words, the relationship can be expressed through the equation. Black hole temperature equals Planck's constant multiplied by the surface gravity, divided by 2 times, p multiplied by the speed of light multiplied by Boltzmann's constant. Although the details of this equation involve several physical constants, the essential message is clear. Black holes possess a temperature. This discovery confirmed Bekenstein's insight that black holes have entropy. Together, Bekenstein's entropy formula and Hawking's radiation result established a deep connection between gravity, thermodynamics, and quantum theory. Physicists soon realized that black holes obey a set of laws remarkably similar to the laws of thermodynamics. The area of the horizon behaves like entropy, surface gravity behaves like temperature, and changes in mass, angular momentum, and charge follow relationships analogous to energy conservation. Researchers such as Robert Wald later refined this framework by developing a more general formulation of black hole thermodynamics. Wald showed that entropy can be derived from the symmetries of gravitational theories, linking thermodynamic properties directly to the geometry of spacetime. Gary Gibbons also contributed to this area by studying black holes using techniques from quantum gravity and Euclidean geometry. His work helped clarify the relationship between gravitational path integrals and thermodynamic quantities. Another intriguing development came from physicist Ted Jacobson. In the 1990s, Jacobson proposed a striking idea. He showed that Einstein's field equations themselves could be derived from thermodynamic principles. By assuming that entropy is proportional to horizon area and applying the laws of thermodynamics to local spacetime horizons, Jacobson demonstrated that the equations describing gravity emerge naturally. In other words, gravity might not be a fundamental force in the traditional sense. Instead, it could arise as a large-scale statistical effect emerging from microscopic degrees of freedom, much like temperature emerges from the collective motion of atoms. This perspective hints that the simplicity of black holes may reflect deeper thermodynamic laws governing spacetime itself. The smoothness of a black hole's exterior and the limited set of parameters describing it might not simply be a feature of gravitational collapse. It may be a consequence of the fundamental statistical structure of the universe. In this view, black holes are not just astrophysical objects. They are windows into the deepest connections between gravity, quantum mechanics, and the thermodynamic behavior of spacetime itself. Black holes appear simple from the outside. Their gravitational field seems to depend only on a few numbers, and the complicated details of the star that formed them seem to vanish behind the event horizon. For a long time, many physicists were comfortable with that picture. But when the ideas of quantum mechanics were combined with black hole physics, something deeply puzzling appeared. The puzzle is now known as the black hole information paradox. To understand the paradox, it helps to begin with a basic principle of quantum theory. In quantum mechanics, the evolution of a physical system is described by equations that preserve information. The mathematical rule governing this evolution is known as unitarity. In simple terms, it means that the complete information about a system's initial state can always be recovered from its final state, at least in principle. Nothing is truly lost. Even if a system evolves into a complicated or chaotic configuration, the underlying quantum information remains encoded in the physical state of the system. A useful way to express this idea is through the evolution of a quantum wave function. The wave function describes the probabilities of different outcomes for a quantum system. The equation governing its time evolution, known as the Schrödinger equation, ensures that information is conserved over time. In words, the equation states, the rate of change of the wave function with respect to time equals the imaginary unit multiplied by the Hamiltonian operator acting on the wave function divided by Planck's constant. Although the mathematical details can be challenging, the essential consequence is clear. Quantum processes do not destroy information. If information were truly lost, the laws of quantum mechanics would have to be modified in a fundamental way. Now consider what happens when a black hole forms. A star collapses, matter falls inward, an event horizon appears. From the outside, the black hole seems to contain only mass, spin, and possibly electric charge. The details of the collapsing matter become hidden behind the horizon. At first, this situation already seems unusual. Information about the original star appears inaccessible to distant observers. But the problem becomes far more serious once Hawking radiation is taken into account. Hawking showed that black holes slowly emit radiation due to quantum effects near the event horizon. This radiation carries energy away from the black hole, causing its mass to decrease over time. Eventually, if no additional matter falls in, the black hole will evaporate completely. The timescale for this evaporation is enormous. A black hole with the mass of our Sun would take roughly 10 to the power of 67 years to evaporate, far longer than the current age of the universe. But in principle, the process does complete. Here is where the paradox emerges. Hawking radiation is thermal. Its spectrum resembles the radiation emitted by a hot object with a specific temperature. Thermal radiation carries very little detailed information about the system that produced it. If a black hole evaporates by emitting purely thermal radiation, then the information about the matter that formed the black hole appears to vanish. Imagine throwing a detailed object into a black hole. Perhaps a book containing a large amount of information encoded in its pages. If the black hole eventually evaporates into featureless thermal radiation, None of the specific details of that book seem to reappear in the radiation. The information appears to be lost. But according to quantum mechanics, that cannot happen. The contradiction between these two ideas forms the black hole information paradox. Stephen Hawking initially argued that black holes genuinely destroy information. In his early analysis, the radiation emitted during evaporation was completely independent of the information contained inside the black hole. Many physicists found this conclusion troubling because it suggested that quantum theory might need to be modified. Other researchers believed that the information must somehow escape. One physicist who explored this question in detail was Don Page. In the early 1990s, Page analysed how information might be distributed in Hawking radiation if quantum mechanics remains valid. He studied the entanglement between the radiation emitted by a black hole and the remaining mass of the black hole itself. Page discovered that if information is preserved, the radiation should follow a specific pattern over time. Early in the evaporation process, the radiation appears almost thermal and contains little information about the interior. But as the black hole continues to evaporate, correlations begin to appear in the radiation. Eventually, the radiation begins carrying more and more information about the original matter that formed the black hole. The point at which the information content begins to increase is now known as the Page time. According to Page's calculations, this moment occurs when roughly half of the black hole's entropy has been emitted through radiation. The pattern of information flow predicted by Page is often illustrated using a graph called the Page curve. The curve shows the entanglement entropy of the radiation rising initially, and then falling as information begins to emerge. If the Page curve is correct, the information contained inside the black hole is not destroyed. Instead, it slowly leaks out through subtle correlations in the radiation. The challenge is understanding how this information escapes. Several theoretical ideas have been proposed to resolve the paradox. Gerard 't Hooft suggested that the information might be encoded on the boundary of spacetime itself. This idea eventually developed into what is known as the holographic principle. The holographic principle proposes that the information describing a volume of space may be stored on a lower dimensional boundary surrounding that region, somewhat like a hologram storing a three-dimensional image on a two-dimensional surface. Leonard Susskind expanded on this concept and applied it to black holes. He argued that the information contained inside a black hole might be encoded on its event horizon. According to this view, the horizon behaves like a kind of informational surface that preserves the quantum details of everything that falls into the black hole. Another major development came from Juan Maldacena. In the late 1990s, Maldacena proposed a powerful theoretical framework known as the anti-de Sitter conformal field theory correspondence, often abbreviated as ADS-CFT. This correspondence suggests that a theory of gravity in a higher dimensional spacetime can be mathematically equivalent to a quantum field theory without gravity on its boundary. In certain models, black holes in the gravitational description correspond to ordinary thermal states in the boundary quantum theory. Because quantum field theories obey the principle of information conservation, this correspondence suggests that black hole evaporation should also preserve information. Taken together, these ideas indicate that black holes may not truly erase the information about their origins. Instead, the information might be encoded in ways that are extremely subtle and difficult to detect. If this is correct, then the simplicity of black holes may be somewhat deceptive. Although the external gravitational field depends only on mass and spin, the deeper quantum structure of the black hole might still contain traces of everything that has ever fallen inside. The information paradox therefore challenges the idea that black holes completely erase their past. Instead, it suggests that the universe may be hiding that information in ways we are only beginning to understand. As physicists continued exploring the information paradox, a surprising idea began to emerge. Black holes might not simply hide information, they might process it. In fact, some researchers began to suspect that black holes could be among the most efficient information processors in the universe. To understand this idea, it helps to consider how information behaves in quantum systems. In everyday life, information can remain localized. A message written on a piece of paper stays on that paper unless it is copied or moved elsewhere. In physics, however, quantum systems behave differently. When particles interact, the information describing their quantum states becomes distributed through a phenomenon known as entanglement. Quantum entanglement links the properties of particles together in ways that cannot be explained using classical ideas alone. When two particles become entangled, Measuring one immediately influences the possible outcomes for the other, even if the particles are separated by large distances. Entanglement spreads information through a system. When a quantum system evolves over time, information that was initially localized in one region can become spread across many degrees of freedom. This spreading process is known as scrambling. Scrambling does not destroy information. Instead, it disperses the information so thoroughly throughout the system that recovering it becomes extremely difficult. A helpful analogy is stirring cream into coffee. At first, the cream sits in a distinct swirl near the surface, but as the coffee is stirred, the cream spreads throughout the cup until it becomes impossible to separate the original drop. The information about where the cream began is still present in the microscopic arrangement of molecules, but retrieving it would require reversing every molecular motion in the cup. In quantum physics, scrambling can occur much more rapidly than ordinary mixing processes. Black holes appear to be especially powerful scramblers. One of the first scientists to analyze this possibility carefully was Patrick Hayden, working together with John Preskill. Their work explored how information might behave when it falls into a black hole. Imagine dropping a quantum system, perhaps a single particle containing encoded information, into a black hole. At first glance, it might seem that the information disappears behind the event horizon and becomes inaccessible. But Hayden and Preskill considered what happens if the black hole has already been emitting Hawking radiation for some time. In that situation, the radiation outside the black hole may already be entangled with the internal degrees of freedom of the black hole itself. Their calculations revealed a surprising result. If the black hole behaves as a fast scrambler, the information contained in the particle may become mixed with the internal quantum states of the black hole extremely quickly. Once scrambled, that information can begin leaking out through Hawking radiation sooner than one might expect. In fact, after a relatively short time, the information may start appearing in the outgoing radiation. The timescale for this scrambling process depends on the size of the black hole. Physicists believe that black holes may scramble information in a time proportional to the logarithm of their entropy. This remarkably short timescale led to a theoretical proposal known as the fast scrambling conjecture. The fast scrambling conjecture suggests that black holes are the fastest scramblers of information allowed by the laws of physics. For a black hole with the mass of our Sun, the scrambling time would be only a fraction of a second. For supermassive black holes at the centers of galaxies, the process might take minutes or hours. Although those timescales sound long in human terms, they're incredibly rapid compared with the enormous lifetime of the black hole itself. Once information becomes scrambled inside the black hole, it becomes encoded in highly complex quantum correlations among the microscopic degrees of freedom of the system. Understanding how this encoding works has led physicists to explore connections between black holes in an unexpected field of study: quantum error correction. Quantum error correction was originally developed for quantum computing. Quantum information stored in delicate quantum states can easily be disrupted by interactions with the environment. Error correction schemes protect this information by spreading it across multiple physical components in such a way that small disturbances do not destroy the encoded data. Remarkably, some of the mathematical structures used in quantum error correction appear to resemble the way information might be stored in spacetime. Physicists such as Daniel Harlow and Ahmed Almeri have explored these connections in the context of black hole physics and quantum gravity. Their work suggests that the geometry of spacetime may behave like a kind of quantum error correcting code. In this picture, information about the interior of a black hole could be encoded redundantly across the surrounding quantum fields. Even if parts of the system are inaccessible, the information may still be recoverable from other regions. This idea links black hole physics to an even more profound possibility. Spacetime itself may emerge from patterns of quantum entanglement. One influential concept along these lines comes from the holographic principle and the theoretical framework known as gauge gravity duality. In certain models of quantum gravity, the geometry of spacetime can be described in terms of quantum entanglement among microscopic degrees of freedom living on a lower dimensional boundary. In these models, the curvature of spacetime corresponds to patterns of entanglement in the underlying quantum system. If entanglement were removed, spacetime geometry could dissolve. This perspective has led physicists to propose that gravity and spacetime might not be fundamental ingredients of the universe. Instead, they may emerge from deeper quantum relationships among microscopic components. Black holes provide an ideal laboratory for studying these ideas because they push gravity, quantum theory, and thermodynamics into a single extreme environment. The remarkable simplicity of black holes at large scales may therefore hide a vast and intricate quantum structure beneath the surface. From a distance, a black hole appears defined only by mass and spin. But inside the horizon, quantum information may be undergoing rapid scrambling, spreading through an enormous web of entanglement that encodes the history of everything that has ever fallen inside. If this picture is correct, then black holes are not merely cosmic vacuum cleaners swallowing information forever. They are among the most sophisticated quantum systems in the universe, mixing and redistributing information in ways that challenge our deepest understanding of space, time, and reality itself. For many years, the idea that black holes have no hair seemed almost unassailable. The mathematics of general relativity suggested that once a black hole settles into a stable state, its external properties depend only on a small number of parameters. Mass, spin, and electric charge appear to capture everything that distant observers could ever measure. Yet the information paradox raised an unsettling possibility. If information cannot be destroyed, and if black holes eventually evaporate through Hawking radiation, then somehow the information about everything that fell into the black hole must still exist somewhere. This tension encouraged physicists to revisit the idea that black holes are perfectly bald. Perhaps they do possess hair after all. Not the obvious kind of hair that would show up in classical gravitational fields, but something far more subtle, something quantum. One intriguing proposal emerged from work by Stephen Hawking, Andrew Strominger, and Malcolm Perry during the 2010s. They suggested that black holes might carry what they called soft hair. To understand this idea, it helps to look at a surprising symmetry hidden within the structure of space-time. In the early 1960s, physicists Hermann Bondi, M.G.J. Vanderburg, A.W. Metzner, and Rainer Sachs studied the behavior of gravitational waves traveling through space-time toward infinity. While examining the asymptotic structure of space-time far away from isolated systems, they discovered an unexpected mathematical symmetry. This symmetry became known as Bondi-Metzner-Sachs symmetry, often shortened to BMS symmetry. BMS symmetry describes transformations that can occur at the boundaries of spacetime without changing the essential physical structure of the gravitational field. These transformations include shifts known as supertranslations, which alter how coordinates are assigned at infinity, while preserving the underlying geometry. For many years, BMS symmetry was treated mainly as a mathematical curiosity associated with gravitational radiation. But later research suggested that this symmetry might carry deeper physical significance. Hawking, Strominger, and Perry explored how BMS symmetry could apply not only at infinity, but also at the event horizons of black holes. Their work suggested that black hole horizons might possess an infinite number of subtle degrees of freedom associated with these symmetry transformations. These degrees of freedom would correspond to what they called soft gravitons or soft photons. The word soft in this context refers to particles with extremely low energy. In quantum field theory, soft particles arise when gauge fields undergo long wavelength excitations. Although these excitations carry almost no energy, they can still encode information about the configuration of fields in spacetime. The soft hair proposal suggests that when matter falls into a black hole, it may leave behind subtle imprints in the form of soft gravitational or electromagnetic modes on the event horizon. These soft modes would represent tiny shifts in the geometry or electromagnetic structure of the horizon itself. From a distance, these shifts would be extremely difficult to detect. They would not alter the large-scale gravitational field in a noticeable way. The black hole would still appear to obey the classical description determined by mass and spin, yet at the microscopic level, the horizon might store a record of information about the particles that crossed it. In other words, the black hole may not be entirely bald after all. Instead, it might possess an enormous number of tiny quantum hairs. Each hair would correspond to a subtle degree of freedom associated with the horizon's symmetry structure. Although individually small, these degrees of freedom could collectively encode vast amounts of information. This idea provides one possible way to reconcile black hole evaporation with the principles of quantum mechanics. If information about infalling matter is stored in soft hair on the horizon, then it might gradually reappear in the Hawking radiation emitted by the black hole. The radiation would carry not only thermal energy, but also delicate correlations reflecting the information stored in the horizon's soft modes. However, the soft hair proposal remains an active area of research. Many questions remain unresolved. Physicists are still working to determine exactly how much information these soft degrees of freedom can store, how that information might influence Hawking radiation, and whether the mechanism is sufficient to fully resolve the information paradox. Some researchers believe soft hair could provide an important piece of the puzzle. Others argue that additional mechanisms may be required. The broader point is that the study of black hole horizons has revealed an unexpectedly rich structure. What once seemed like a simple boundary separating the interior of a black hole from the outside universe may actually contain a complex web of quantum degrees of freedom. The smooth horizon predicted by classical general relativity might hide an intricate microscopic landscape shaped by quantum fields and space-time symmetries. If that is true, then the statement that black holes have no hair may need to be interpreted carefully. At the classical level, the statement appears to hold. The large-scale gravitational field of a black hole is determined by only a few parameters. But at the quantum level, the horizon itself may carry far more information than classical theory suggests. Whether this information truly resolves, the paradox remains uncertain. What is clear is that the simple phrase introduced by John Wheeler continues to inspire deeper investigation. Black holes may look smooth and featureless from a distance, but as physicists probe the boundaries of space-time more closely, they are beginning to suspect that even the smoothest cosmic objects may hide subtle textures beneath the surface. For more than a century, Einstein's theory of general relativity has provided the foundation for our understanding of gravity. The theory has passed an extraordinary number of experimental tests, from the bending of light around the sun to the precise motion of planets and the detection of gravitational waves from merging black holes. Yet physicists are always cautious about declaring any theory complete. General relativity works extremely well on large scales, but it struggles to merge with the laws of quantum mechanics. It also leaves open questions about dark matter, dark energy, and the behavior of gravity at extremely high energies. Because of these open questions, researchers have explored many alternative or extended theories of gravity. These theories modify Einstein's equations in subtle ways, often by introducing additional fields or new interactions that could influence space-time under extreme conditions. One fascinating possibility is that these modified theories could produce black holes that do have hair. Not the classical hair imagined in early debates, but additional fields surrounding the black hole that alter its structure in measurable ways. In Einstein's theory, gravity is described entirely by the curvature of space-time, represented mathematically by the metric tensor. But some extended theories introduce extra fields that interact with gravity. One common example is a scalar field. A scalar field assigns a single numerical value to every point in space and time. Temperature in a room is a familiar example of a scalar field. In theoretical physics, scalar fields often appear in attempts to unify gravity with other fundamental forces. If gravity couples to a scalar field, the structure of black holes can change. The black hole may develop what physicists call scalar hair. Scalar hair refers to the presence of a scalar field surrounding the black hole, extending beyond the event horizon and influencing the geometry of space-time. This additional field could alter the gravitational field of the black hole in subtle ways that differ from the predictions of general relativity. Several researchers have explored these possibilities in detail. Thomas Soteriou has studied scalar tensor theories of gravity, which extend Einstein's theory by coupling space-time curvature to scalar fields. His work has examined how these fields could modify the structure of compact objects, including black holes and neutron stars. Paolo Pani has also contributed extensively to the study of black hole solutions in alternative gravity theories. His research explores how deviations from the Kerr solution might appear in gravitational wave signals. Takaaki Tanaka and Hector Silva have investigated similar questions, analyzing how scalar fields can form stable configurations around black holes under certain conditions. Together, their work suggests that some modified gravity theories allow black holes to possess additional observable properties beyond mass and spin. One example of such a framework is scalar tensor gravity. In scalar tensor theories, gravity is mediated not only by the curvature of space-time, but also by a scalar field that influences how gravity behaves. These theories were originally developed in attempts to generalize Einstein's equations and explore possible variations in gravitational strength. Under certain circumstances, scalar tensor gravity can produce black hole solutions with scalar hair. Another intriguing extension is known as Einstein-Dilaton-Gauss-Bonnet gravity. This theory arises in certain models of string theory and introduces higher curvature corrections to Einstein's equations. In this framework, gravity interacts with a scalar field known as the dilaton, and the equations governing spacetime include additional terms related to a geometric quantity called the Gauss-Bonnet invariant. These additional terms modify the structure of black holes. Instead of the simple Kerr geometry predicted by general relativity, the resulting black holes may carry scalar fields that extend beyond the horizon. These fields could influence the motion of matter near the black hole, alter the pattern of gravitational waves emitted during mergers, or slightly change the structure of the event horizon. From a distance, such black holes might still appear similar to ordinary ones, but careful measurements could reveal subtle differences. For example, the frequencies of gravitational waves emitted during the ring-down phase might deviate slightly from the predictions of the Kerr solution. The multipole moments of the black hole could differ from those expected in general relativity. Detecting such deviations would be extraordinarily important. It would provide evidence that Einstein's theory is not the final description of gravity. Instead, it would point toward a deeper framework incorporating additional fields or new physical principles. This possibility is one of the reasons why gravitational wave astronomy has become such an exciting field. Modern observatories such as the Laser Interferometer, Gravitational Wave Observatory and the Virgo Detector allow scientists to study black holes in ways that were impossible just a few decades ago. Future observatories promise even greater sensitivity. Projects such as the Laser Interferometer Space Antenna, often abbreviated as LISA, will place gravitational wave detectors in space, allowing them to observe signals from supermassive black hole mergers across the universe. Ground-based observatories planned for the future, including the Einstein Telescope and Cosmic Explorer, will also improve our ability to detect subtle features in gravitational wave signals. These instruments will measure the vibrations of black holes with extraordinary precision. If black holes truly follow the simple predictions of general relativity, their signals will match the patterns expected from the Kerr geometry. But if additional fields exist, or if gravity behaves differently under extreme conditions, those signals may reveal small but measurable differences. In that case, the discovery of hairy black holes would not merely modify a detail of astrophysics, it would transform our understanding of gravity itself. For now, Einstein's theory continues to pass every observational test with remarkable accuracy. Yet the possibility remains that somewhere in the universe, under the most extreme conditions imaginable, gravity might reveal a slightly more complicated story. And if that happens, the bald simplicity of black holes may turn out to be hiding a few unexpected strands after all. The study of black holes has moved from abstract mathematics to direct observation with remarkable speed. For most of the 20th century, black holes existed primarily in equations, theoretical papers, and the imaginations of physicists. Today, they are becoming some of the most carefully measured objects in the universe. This transformation has been driven largely by the rise of new observational technologies, especially gravitational wave astronomy. The first detections made by the Laser Interferometer, Gravitational Wave Observatory, opened an entirely new way of observing the cosmos. Instead of studying only light from distant objects, scientists can now measure tiny ripples in spacetime produced by massive cosmic events, and those events often involve black holes. When two black holes orbit each other and merge, they release an enormous burst of gravitational energy. In the final moments before the merger, the pair can radiate power greater than the combined light output of all the stars in the observable universe. Although that energy travels outward as gravitational waves rather than visible light, modern detectors are capable of measuring the resulting distortions. The success of these early observations has inspired an ambitious new generation of instruments. One of the most exciting projects is the Laser Interferometer Space Antenna, commonly known as LISA. Unlike ground-based detectors, LISA will operate in space. The mission will consist of 3 spacecraft arranged in a giant triangular formation, separated by millions of kilometers. Laser beams will travel between the spacecraft, forming an enormous interferometer capable of detecting gravitational waves with much longer wavelengths than those observed on Earth. These long wavelength signals are produced by extremely massive objects, including supermassive black holes residing at the centers of galaxies. When two galaxies merge, their central black holes eventually spiral together and collide. Such mergers release gravitational waves that can travel across billions of light years. LISA will allow scientists to observe these colossal events in extraordinary detail. On Earth, several other next-generation observatories are also being planned. One of these is Cosmic Explorer, a proposed detector in the United States designed to be significantly larger and more sensitive than the current LIGO facilities. Cosmic Explorer would use interferometer arms stretching tens of kilometers in length, allowing it to measure gravitational waves with far greater precision. Another planned instrument is the Einstein Telescope, a European project that would place a triangular interferometer deep underground. By isolating the detectors from surface vibrations and environmental noise, scientists hope to achieve extremely sensitive measurements of gravitational waves. These new observatories will dramatically increase the number of black hole mergers that astronomers can study. Instead of detecting a handful of events each year, future detectors may observe thousands or even tens of thousands of mergers across the universe. With such large datasets, physicists will be able to examine the properties of black holes with unprecedented accuracy. One of the most important goals will be testing the Kerr solution of general relativity. If black holes truly have no hair, their gravitational wave signals must match the precise patterns predicted by the Kerr geometry. The frequencies of the ring-down vibrations, the multipole moments of the spacetime geometry, and the detailed shape of the gravitational wave signal must all follow the relationships derived from Einstein's equations. But if any deviations appear, even tiny ones, they could reveal new physics. A slightly different ring-down frequency might suggest the presence of additional fields surrounding the black hole. An unexpected multipole moment could indicate that the object possesses some form of hair not predicted by classical general relativity. Detecting such differences will require extremely precise measurements. That is why the next generation of detectors is so important. Gravitational wave observatories will not be the only tools available to astronomers. Other methods of studying black holes are advancing rapidly as well. One of the most remarkable recent achievements came from the Event Horizon Telescope collaboration. This international network of radio observatories links telescopes across the Earth to create a virtual instrument the size of our entire planet. Using a technique known as very long baseline interferometry, the Event Horizon Telescope can resolve structures near the event horizons of supermassive black holes. In the year 2019, the collaboration released the first image of the shadow of a black hole located in the galaxy Messier 87. A few years later, another image revealed the shadow of the supermassive black hole at the center of our own Milky Way galaxy. These observations provide a direct glimpse of the region, where gravity becomes extraordinarily strong. Astronomers have also been tracking the motion of stars orbiting close to the black hole in the center of the Milky Way. Two researchers who played leading roles in this work are Andrea Ghez at the University of California, Los Angeles, and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics. By carefully measuring the orbits of these stars over many years, their teams demonstrated that a compact object with millions of times the mass of our Sun resides at the center of our galaxy. The object's gravitational influence matches precisely what would be expected from a supermassive black hole. Another scientist deeply involved in observing black holes is Shep Doeleman, who helped lead the Event Horizon Telescope project and contributed to the development of the techniques that made those images possible. Together, these observational efforts are turning black hole physics into an empirical science rather than a purely theoretical one. With each new observation, astronomers gain a clearer picture of how black holes behave in the real universe. The coming decades promise even more dramatic discoveries. As gravitational wave detectors grow more sensitive and astronomical instruments continue improving, scientists will be able to examine black holes in ways that were once unimaginable. They will measure the vibrations of space-time itself. They will observe matter swirling near event horizons, and they will test whether the elegant simplicity predicted by general relativity truly holds under the most extreme conditions in nature. Perhaps the results will confirm Einstein's theory once again, reinforcing the idea that black holes possess only a few defining properties. Or perhaps subtle discrepancies will appear, hinting that the universe still has deeper secrets waiting to be uncovered. Either way, the quest to understand black holes continues, and with it the search for the true nature of gravity, space-time, and the information hidden within the darkest regions of the cosmos.